Hi, I'm Nora Castner, and welcome to my talk on deep semantic gaze embedding and scanpath comparison for expertise classification during OPT viewing. This is a panoramic X-ray of the teeth, or OPT, and this image looks pretty straightforward to you and me. You wouldn't think that there are any anomalies. However, there are actually quite a few, and of varying difficulty. And though these images are part of routine examinations for dentists, they're still very difficult to interpret. And in order to understand how professionals interpret these images, we can use eye tracking as an objective measure. This way, expert cognition can offer support for student training or even AI development. Even from this example, there's apparent differences in expert and novice scan paths. Within the first 18 seconds, the expert, in blue, has covered more of the image with long sweeping saccades of the outer area before honing in on an area that has caught his attention. Whereas in the same time frame, the novice, in orange, has only focused on the teeth area, making small saccades to each tooth and completely neglecting these outer areas. We can use scan path analysis to compare the similarity of scan paths, to cluster behavioral patterns, or to classify novices and experts. This work furthers understanding of expert medical image inspection by using data-driven approaches, and we use these approaches for expertise recognition and semantic extraction. We focus on a particularly underrepresented domain of dentistry. So far, there's only really been 4 studies that look into the differences of expert and novice dentists. And ultimately, we want to use this information for better development of intelligent tutoring systems or decision support systems. There are many approaches to scan path analysis, and if we want to focus on these semantics, these what are they looking at, we tend to use areas of interest, or AOIs. And one well-known method that uses these AOIs is string alignment. String alignment compares how similar 2 strings are to one another. A scan path is mapped to AOIs, which encodes it to a character sequence. Sequences can either be globally aligned, for example, by using the Needleman-Wunsch algorithm, or locally aligned, by using, for example, the Smith-Waterman algorithm. Both return a similarity score based on how little the sequences or subsequences need to be manipulated. These methods are still the gold standard as they're easy to implement and return the most optimal alignment of all possible alignments. But using AOIs has a caveat. They can be tedious and subjective to define. So we want the semantics, but without the effort. Our approach looks at the fixation behavior. This way, we can recognize similar image semantics or meaning, like the left jaw joint, when 3 different subjects are looking at it and in 3 separate images. As you can see here, from the higher the color, meaning more similar the patch is. And thus, this is a high-level representation of what they're looking at. So our approach, Deep Scan, takes image patch information at the fixation level. As you can see here, these are the fixations of a subject. We extract a 100 pixel by 100 pixel patch of the image around the center of the fixation. We maintain the temporal order, and we run each image patch through the VGG16 network. And a feature vector is then extracted from this network, and we can use these feature vectors to build a matrix that is the sequence of the scan paths. So similar to a string of characters, we have now a string of feature vectors. And from this string of feature vectors, we can compare this to another scan path. We use the Smith-Waterman algorithm for local alignment, but we replace the string of characters with the string of feature vectors. and we can compare them against each other. But we'll never necessarily have a match between the feature vectors, so we can only get a difference between them. But we still need a baseline to get the similarity in the overall context. So we compare this difference of the feature vectors to a baseline C. For this, C was the average feature vector difference calculated from scanpaths for a random image. A brief description of the data set: we used incoming 6th-semester dental students taken from a larger cohort study. These students have a basic understanding of dentistry, however, no targeted training on OPT inspection. Experts were from the university clinic and had on average 10 years of professional experience. Both groups were asked to inspect the OPT images, and their gaze and their anomaly detection performance was measured. And experts definitely outperformed the students. Based on the similarity of subjects averaged over all images, we were able to get 2 distinct clusters using unsupervised clustering. A mainly expert cluster where only 4 students wound up here, and a majority student cluster where only 1 expert was found to be in this cluster. This gives us about a 94% accuracy. And from this, we can say that experts have highly similar patterns to each other. Thus, they look at image features similarly across all stimuli, whereas students are less similar to each other, and they have much more variable gaze behavior over images. We also compared our method DeepScan to the traditional Smith-Waterman algorithm using manual AOIs indicating the anatomical structure of the OPTs. We used leave one image, one subject out cross-validation for a KNN classifier, and we found comparable performance. DeepScan at 73% accuracy, manual AOIs with the Smith-Waterman at 77% accuracy. Thus, comparable performance, but without tedious labeling. And I want to point out that the manual labeling needed to be done by an expert who understood the anatomical structures of these images and was able to map them appropriately for all images. Thus, comparable performance without tedious labeling and less than half of the effort. And DeepScan is actually quite interesting because also it performs very well for images and subjects that are unseen to the model, thus perfect for intelligent tutoring systems. So this work has gained insight from a large data set working towards data-driven expertise recognition. And this end goal is automated scanpath classification with cross-image feature recognition, task applicability, and ultimately online capability for intelligent tutoring systems. Thank you for your attention.